Okay, so we're going to continue getting into the modular space of these torus-like objects, also quantum torus and quantum toric manifolds or spaces. I don't even know what the appropriate name is for these quantum toric spaces. I guess quantum toric stacks is not too bad. Yeah, they generalize toric varieties, as we will see. In the case, I just remind you very, very quickly that we have the quantum torus. So the quantum torus was meant to be an algebra, a non-commutative algebra that had xy equals e to the 2 pi I h yx. But this was realized as was meant to be the algebra of functions on the space of leaves of the Kronecker foliation. So we had the Kronecker foliation. We form somehow the space of its leaves. And this is the algebra of functions on the space of the leaves of the Kronecker foliation. So, but because we could take a transversal here, this could be construed as the stack of the torus divided by the action in this real picture of R on the torus, but by the image of this exponential of slope h bar, or it could be the transversal divided by the rotation group z h bar z. Here maybe I should write h bar h r. And so this could also be construed as c divided by the lattice generated by 1 and h bar inside, this is gamma, inside of R, inside of C. So there is these three ways of seeing the quantum torus, and they pass to any dimension, of course. So that was the quantum torus. That's on the previous talks. So a definition of quantum torus is the analytic stack that is a quotient of CD by the action of a finitely generated subgroup gamma of RD. Such a finitely generated subgroup gamma we will call a quantum lattice. It's not a lattice in the traditional sense. Some people would call it a quasi-lattice. It is a quasi-lattice, and we will call it a quantum lattice. We will require that it generates all of RD. So it is the stack CD mod gamma, the analytic stack over the analytic side. And a lemma is that a quantum torus endowed with the operations induced by the this is, after all, a Lie group, CD. So it becomes it's kind of a Lie group. A quantum torus is kind of a Lie group, but it's a stacky version of a Lie group, and it's abelian, and this is called an analytic Picard stack. The precise definition of analytic Picard stack is in topos theory and cohomology, and mental cohomology of schemes by Artin, Grothendieck, and Verdier. So this is the analog of an abelian Lie group in the world of stacks, analytic stacks. And quantum tori, all of them, form a category, TQ, whose morphisms are Picard stack morphisms, which we will call toric morphisms. Now, there is a definition for these morphisms in terms of the theory of stacks, but there is this lemma that lets you forget about all this theory of stacks, let you forget about it in this particular case of quantum torus. So the category of quantum torus, TQ category, this category has quantum tori there and has morphism of quantum tori. But this is equivalent to a much more concrete category. There is another category called the category of quantum lattices that is equivalent. The category of quantum tori is equivalent to the category of quantum lattices, but this one, the second one, is very concrete. It doesn't use all this stacky or Picard stack or anything like that. And so there is this theorem or lemma or proposition that says that the category of quantum lattice are inclusions of finitely generated groups gamma inside of RD together with the inclusion that generate all of RD, and the morphisms are just linear maps linear given by a matrix, linear maps from Euclidean spaces that restrict to group morphisms and these abelian group morphisms from gamma to gamma prime. And this is an arrow. This is a morphism in Q lattice, an arrow in Q lattice. And now this category is very concrete. Its objects are just, these are the objects. These are the objects. These are the arrows. It's very concrete now. It's not, and it's equivalent to the category of quantum torus. And this category we want to enhance to complete to the category of quantum toric stacks or quantum toric spaces. But now this is very concrete. So I can put under the rug all this Picard stack story by using this theorem or proposition. Anyway, we already had seen quantum P1. Quantum P1, we get this quantum torus, and poetically, or something like that, we compactify, we add 2 points, and then we, I don't know what to draw, you know. We add 2 points, we compactify, and that's the way we get this. But of course, we want the whole thing to still be smooth in a certain sense, and analytic, and want to be analytic. Want still to be those things. We cannot just take the kind of the suspension with singularities at the, like I draw it here. We want it to be nice. Well, you do the obvious thing, you know. Here you get this quantum torus. that by the equivalence of categories can be identified more or less with the quantum lattice. But anyway, here is the quantum torus, and here is the same quantum torus after an automorphism. So this is an automorphism of the quantum torus to be expected. And notice that this automorphism is the same one that I use to, given the usual complex torus, the usual complex torus, to glue CP1. To have this automorphism is the same as to have the gluing for CP1. Well, now I have this automorphism of the quantum torus, but the quantum torus is easily partially compactified because this quantum torus here is inside this thing easily. And it is partially compactified. And now I have two copies of partially compactified quantum tori, and I can glue them together easily, and I get quantum P1. Notice that in the classical torus, pi1 of C star is Z. That is the lattice that is occurring here. You know, C star is after all equals to C mod Z. And here the group that takes the place of Z for the CP1, and this becomes by transgression pi2 of CP1, is gamma. It wants to be. But of course, this is not literally true only literally true in the sense of stacks. And again, I have already talked about this dimension counting in the past. I will just say that because we have this T2 and this action of C given by H bar in T2, this is dimension 1, so a very naive counting would give you 2 minus 1 equals 1. But this is not the correct dimension count because C1 is contractible. So if I take the homotopy quotient that counts the correct stacky dimension, so what is the homotopy quotient? Well, I take the homotopy quotient of the action of a group on a space, the Borel construction or homotopy quotient is by definition this is not just X mod G, it's X cross EG, where EG is contractible, so that homotopically does nothing, but it frees up the action. But G acts on EG freely. It's a free action. Well, in the case of an R action, the computation of EG for G is it's an interesting thing in general. For example, if G was the simplest possible group, Z2, EG would be, well, the infinity sphere, and the quotient of EG by G, it's called BG, would be CP infinity.
RP.
RP infinity, sorry. But for R, if G is R, well, there is an obvious contractible space where R acts. R acts. Well, what is your guess, Misha? R acts on what? On what space?
R.
On R by itself, freely. So ER is just R. And here I get T2 cross R mod R. But of course, the action is diagonal. That's the important thing. But now the action is free. T2 cross R, and this is the homotopy quotient. And this is the correct homotopy type for the quantum torus. That is a stack. So the most basic topological invariants of the stack are represented by this space, where R acts by the diagonal action here. And this already computes correctly the periodic cyclic homology and so on of this space. And it's a two-dimensional space. This is two-dimensional. And this is the correct topological type of the stack, not just the non-Hausdorff. The non-Hausdorff space T2C mod C is not the correct topological type. It's, well, T2C cross EC C cross E. R is acting. R is the correct topological type. And this computes the correct topological invariance. And it's of dimension 2. So that's the correct dimension counting. But there is something else going on that is kind of nice. And I would say it a little bit differently today than what I say here. There is, let me move this one. There is the following. The thing is that I have this complex torus that I'm drawing real, and I have this complex foliation by C leaves in the case of the two torus, or D minus one dimensional leaves. I have that. And when I do CP1, but I want to do it complex analytically, what I want to do somehow is to get a manifold N that contains the torus but that is a complex manifold. It's a complex manifold. It contains the torus, and the foliation the Kronecker foliation that we have here extends to a foliation. The Kronecker foliation extends, I don't know what to call it, extends to a foliation in all of N. But N is a compact complex manifold. N is a compact complex manifold that contains the open torus and compactifies it, but also this foliation, the Kronecker foliation, extends to a holomorphic foliation, an analytic holomorphic foliation. So the foliation is holomorphic. And so that CP1 becomes itself the space of leaves of the foliation. And now, in a foliation sense, it is that CP1 contains T1. And of course, here the problem is with these two. It's traditionally called T2, but I should call it T1 or T2. It looks very funny, this situation, but it is the way it is. So we have the torus, the complex torus, and CP1 will compactify by extending to a complex manifold the foliation. In fact, for the classical Kronecker foliation in C star cross C star, that contains S1 cross S1, the thing I'm drawing, the manifold N that does this, in fact, the manifold is itself independent of H bar, the manifold N. It's independent of H bar. What is moving with H bar is the foliation. What is moving with H bar, and now I'm starting to speak about moduli. As I move H bar, I will create moduli of these objects, but n will mostly remain fixed. In any case, n happens to be S1 cross S3. S1 cross S3 is an elliptic fibration over P1, classical P1. And this is an elliptic fibration with elliptic curves above every point of P1. We have elliptic curves. And it is very interesting that this is the situation for H bar equal to 0. The classical situation, this manifold is well known, is called the Hopf manifold. And if I forget about S1, if I forget about S1, what I have is P1 S3 above. I have a topological situation. S3 about S2 above S2 with fiber S1. This is the Hopf fibration. But if I multiply the Hopf fibration by S1, I complexify it. This one it was already complex. I do nothing. This is P1. S1 cross S3. S3 is not a complex manifold, and S1 is not. They are odd dimensional. They couldn't be. But S1 cross S3 is a complex manifold, the Hopf manifold, and it fibers over P1 by elliptic curves. But this is the situation H is equal to 0, and it's classical. It's the Hopf fibration. And its complexification, the elliptic fibration of the Hopf surface. Now, what is very interesting is that I perturb H bar and I make it different from 0. Now, N lives above P1H. N lives above P1H, extending, but it has a foliation now. Now the fibration is not by E, it's by C. Here it was also by C, but we were confused. It was by E because by coincidence the C closed on itself rationally. But in the irrational case, C doesn't close on itself, and I get this fibration, but this elliptic fibration becomes the foliation that extends the Kronecker foliation. So it becomes a foliation that extends the Kronecker foliation. So let me stop 1 second and ask you if this is more or less clear.
Yes.
So it's a very beautiful, huh?
It's more or less clear, yes.
Yeah. It's a very beautiful story. The elliptic fibration, as you perturb it, becomes the compactification of the Kronecker foliation. And this is a big surprise. And this is one of our discoveries. The elliptic fibration was very well known. The Kronecker foliation was very well known. But this relation between the Kronecker foliation and the classical elliptic fibration on the Hopf manifold, it was kind of like, something is going on. So anyway, CP, the quantum version is perturbing H equal to 0, and the classical version will look like the elliptic fibration. But of course, CP1, 0, will not exactly be P1. It will be a germ over P1. And what do I mean by this? That if I see CP1, 0 like this, is P1 in the category of complex manifolds, but not in the category of stacks. In the category of stacks is P1 together with a set stabilizer at every point. And this stacky-wise is written like this. All this says is that as complex manifolds, they are the same. because this doesn't exist as a complex manifold. In fact, this has the homotopy type of a circle. But it's not. But it's just a stack, an algebraic thing. And so all this is reading that above every point in P1, this action has a stabilizer Z. That's what this is saying. And this is so called a germ over.
Does it mean that your resulting manifold has a higher dimension, like it's three-dimensional, or still your dimension count tells you that it's it's a complex curve?
Well, saying I'll say it a little bit better in a second. I'm recovering P1 together with extra information. But it turns out that P1 always knew this extra information. P1 always knew its own second homotopy group. This is the second homotopy group of P1. And it always knew it. So it turns out that as I recover all toric varieties by this procedure, the category of toric varieties and the category of calibrated toric varieties will be equivalent. Having P1 and having P1 with this vibration is the same because P1 always knew this vibration in its topology. So I didn't gain any information. And morphisms of P1s with traditional toric morphisms of PNs and whatever carry these vibrations naturally. So I didn't gain any information in the morphisms either. So it is the same to have P1 toric, not complex manifold, as it is to have P1 together with this germ. You see what I mean?
Yes.
So it's kind of an artifact of the fact that it's really a toric story, the story I'm telling, or a tropical story if you prefer, the story I am telling. But I will, in further examples, will be a little bit more clear. Further examples are already here, of course, and here they are. Hopf manifolds are well, they look like this, and they have also elliptic vibrations here. This is a typical Hopf manifold. This is a typical Hopf manifold. But when I call the Calabi-Ekman, sorry, manifold. But when I call it Calabi-Ekman, I'm stressing that it is a complex manifold. Of course, Hopf manifolds are Calabi-Ekman manifolds of the form S1 cross S3. Or S1 cross S2 minus 1, also called Hopf manifold. Anyway, Hopf manifolds, notice that both Calabi and Hopf manifolds, notice that both Calabi-Ekman manifolds and Hopf manifolds are complex compact manifolds. But are they are not algebraic varieties, complex algebraic, I mean. They are real algebraic varieties. They are not complex algebraic varieties. They are not Kähler. And they are not symplectic. And, well, if they were algebraic, they would be Kähler. And if they were Kähler, they would be symplectic. So if they were algebraic, they would be symplectic. But then you would have a symplectic form. So this symplectic form wants to live inside H2, but this is 0. So there is no symplectic form for topological reasons. So they are not algebraic, Kähler, or symplectic. But they have this elliptic fibration. It's an elliptic holomorphic fibration, and they live above toric varieties. And then you would have the same story. If I perturb a little bit this vibration, then I get a foliation. Depending on a parameter, sorry. But now the quotient will be quantum projective spaces. But of course now the parameter has two h's, h1 and h2. So there's two Planck constants in this deformation. I have 2 degrees of freedom to deform this holomorphic elliptic fibration. Well, it turns out that Laurent Mersenne and Alberto Berkowski in 2004 generalized this picture, and they found a manifold, a complicated manifold, that is product, typically is product of spheres, then connected some with products of spheres, products with spheres, connected some with spheres, I don't know, connected some with the same, it's that kind of thing. It's complicated, but it's a complex manifold. And one of these for every complex toric variety. And the fiber is no longer an elliptic curve, but it is an abelian variety. I don't know what to call it. It's topologically it's a torus, but it's an even torus. But of course, it is a complex manifold, an abelian, and this is an algebraic abelian variety. This is algebraic, but this is not algebraic. But it is a complex manifold that generalizes the Calabi-Ekman manifolds for every toric variety. And this was 2004. And these are called the LBM manifolds. Well, that's very interesting. This picture generalizes to every toric variety. But of course, now you have a lot of degrees of freedom for the deformation of the foliation that extends the Kronecker foliation. This contains a torus. This contains a torus, a complex torus. I don't know what dimension. And I deform this by holomorphically linearly, deform this foliation. I get exactly the Kronecker foliations here, and I get foliations that deform this toric variety in what I call a quantum toric variety. You see what we're doing?
Yes.
So now we have the quantum toric variety. That is the compactification of this Kronecker foliation picture. Here I explain what I already explained. When H is rational, the situation is more delicate than when H is not rational. When H is not rational, you don't have this factor here, because there is no stabilizers. It's just a bona fide stack, Problem is when H is rational, the stack kind of splits off into a purely algebraic part and a classical variety. So when H is rational, the picture looks, you have this R cross R cross R cross R fiber. That really becomes a CM fiber. And you have these LBM manifolds. And you have this, well, quantum toric stack in general, irrational. But then all of a sudden H becomes rational when you are deforming. And then this stack kind of splits off, breaks into a BZ cross Z cross Z cross Z cross Z in general. And then there is this stack that kind of has this all of a sudden vibration into a variety and this part. And this variety is just a complex orbifold. In general, in this case, it's just P1. And these are the classical toric varieties. The H bar rational. And what interpolates between the classical toric varieties, together with this information that they know in its topology, this, in fact, if I take the topological homotopy types, the homotopy types of these stacks, then this indeed becomes just some space. It's the Borel construction that I mentioned before, this homotopy quotient construction, and this becomes just the twofold homotopy cover of X. It becomes just the twofold. So it knows its twofold homotopy cover, and it knows its second homotopy group, that is Z cross Z cross Z cross Z. As many spheres as sides has a polytope if it came from a polytope. So Z cross Z cross Z cross Z. Well, it's not Z cross Z. It's B. In this case, it's B. It says 1 crosses 1 crosses 1 crosses 1 crosses 1 crosses 1 for the second homotopy cover. Anyway, this can be said in this topological fashion, but it can be said stacky-wise, just saying that there is this stack, this funny stack, whose space, underlying space, is a point, but it has all these Z automorphisms. Then there is the stack, and there is the classical toric variety in the rational case. This is the rational H bar. And the irrational one doesn't have this problem. So this is called a gerb. This is called a gerb over X. It's called a gerb. Now, remember that we had the. How much time do I have, Misha?
Well, 5 minutes would be okay.
Well, let me just say this one slide, and then I'll continue, slide 24, and then I'll continue next week. I already said, let's see how this looks in practice, because this is very abstract thing, And how do we say this in practice, in this very linear algebra kind of way? Remember that we had quantum torus was equivalent to the category of quantum lattices as categories. But this was a very simple category where a typical arrow looks like this. Well, not a simple category, a simple to-state category, a simple to-state category where the arrows look like this. And this was just a finitely generated abelian subgroup of RD. But what if I want to put this gerb just in the quantum torus, this gerb thing that I just mentioned, dealing with the rational and the irrational case of the quantum torus? It also has two cases, the rational and the irrational case, the quantum torus. And I want to form a nice modular space of quantum lattices. This is not going to do it, to form a nice modular space. It's going to be a bad modular space of quantum lattices. So I have to put the gerb to form a nice modular space of quantum tori, a nice modular space of quantum lattices. So I'm going to enhance the category of quantum lattices to the category of calibrated quantum lattices. So it's the category, there is a finitely generated group, gamma, there. There it is. It's a finitely generated. But now it comes with a lot of bells and whistles. Let me take this thing away. Now it comes with lots of bells and whistles. So let's see. What is a calibrated quantum lattice? A quantum lattice was just a finitely generated group of Euclidean space. a calibrated quantum lattice is an h from z to the n to rd, and this sends each one of these vectors to the essentially the generators of gamma. A little bit more, I'll explain. But essentially think, at first level of approximation, the whole point is that gamma is the image of H. So I don't. If I have this finitely generated group, I insist in seeing it as the image of a nice lattice of a higher dimension. Typically, n is bigger than d. Typically, n is bigger than d. And I'm also going to have this combinatorial information that is going to become very, very, very important. And right now, maybe a little bit unmotivated, but you'll see that it makes sense for forming a nice modular space. This is a little bit like the mark points of the classical space of curves. It plays the role of these mark points that make the modular space nicer. At first, it looks kind of funny when you're studying the modular space of curves. You know, Riemann didn't have mark points. You say, what are these mark points? It's just like a very silly device. But then it turns out to be extremely convenient. Well, this J is like the mark point device in the modular space of curves. It will make the modular space nicer. And so we want the gamma to be generate of all of RD. We don't want gamma to be inside of R or anything, of a subspace. We want gamma to be all over the place. And so we have these pairs of H, J. And a morphism, so this is my substitute for gamma. I went from gamma and I promoted it into a pair H, J. And a morphism in the past was a linear mapping RD that restricted to gamma. Well, now it's a linear mapping that and a mapping of lattices, a mapping of an arithmetic object, an arithmetic matrix. So this one day will be the origin of a GLNC in our modular space. This will be the origin of GLNC in our modular space. For now, it's a definition. A linear mapping on H and a combinatorial mark point preserving gadget so that LH is the obvious. For I not in J, H of EI is in the sum of I not in J's of Z. And for I in J, I just send the basis to the basis. And it's just like
one question. You do all that to incorporate those gerbs in this picture, right?
That's right.
Okay, very good.
But it becomes very, very natural. It becomes, as you do it more and more, you realize it was inevitable. This is the right thing to do. Otherwise, the modular space is horrendous. And now the modular space is super nice. Just like with curves, this is the equivalent of the Maxim's discovery of the stable curve mapping compactification of curves. Stable maps, you know. This is the analog of that story in the Toric universe.
Okay, it's sort of clear.
You'll see how it,
yeah,
you'll see how it works. Yeah, we will do lots of nice things. But right now, I leave you with the category calibrated quantum tori that is equivalent to the category calibrated quantum lattices. Now it turns out that if you have a calibrated quantum lattice, you can get a quantum tori that is the same as a quantum tori when it's irrational, But it's a quantum toric together with its germ when it's rational, and this is the gadget that does it. And so, and this category calibrated quantum lattices is equivalent to the category of calibrated quantum tori. And we'll continue next time. Thank you very much.
Thank you so much.
Very well. Let's stop the record.